Hello everyone, I am Simone Dominico from the Federal University of Paraná in Brazil. I'm very happy to present a part of my research named Performance Analysis of Array Database System in Non-Uniform Memory Architecture. Today, I talk about the array database systems and the new architecture, our methodology used in our work, experiments, and finally the conclusion. The array database model is used to store and analyze scientific data. In comparison to traditional relational model, the array database implements multidimensional data models to serve many applications that do not fit the traditional relational model. For example, the data presented correspond to temperature changes over the years in a given location, identified by longitude and latitude. In this figure, the data are represented in the relational model, with rows and columns. The other figure represents the multidimensional model. The blue box shows the same data in the relational model and the multidimensional model. The relational model is not ideal for store and analyze scientific data due to its limitations and incompatibility to work directly with the data format generated in scientific application. The incompatibility between the array and the relational model requires a series of data transformations to execute queries to analyze scientific data. So, along with the array data model concept, a wide range of array databases has emerged. It started with the Hasdaman in 1989, after Tyan in 1996, and then ArrayDB in 2000, followed by SH in 2008, after SciDB in 2009, the most cited array database in the literature, after the most recent Kronos in 2018 and Savemi in 2019. At the same time, high-performance systems use new architecture to leverage the high number of CPU cores within the same shared memory. The NUMA architecture is formed by multi-core nodes connected by interconnection links. Each node has its memory bank that can be accessed by all nodes in the architecture. Access to cache memory or local DRAM has a lower latency cost. The remote access in the last level cache is 3 times the cost. Finally, the most expensive access is remote DRAM, approximately twice the cost of accessing local memory. In our research, we showed that the difference in latency costs affects the performance of array database system. The array database systems store the array in small pieces called chunks. An array can have many chunks that are processed during the query running. In the parallel execution, the chunks are processed by multiple threads. The threads are pinned in the NUMA architecture by the operating system. The OS distributes threads in the available cores. This OS not considering the latency cost or if there are remote access. Also, the OS does not know the database operations characteristics to decide the best thread pinning. Observing this behavior, we analyze the impact of the new architecture on an array database. We analyzed 5 well-known thread pinning strategies that are used in our experiments include a processing core allocation mechanism to support the thread scheduling and the data allocation across NUMA sockets, and the random allocation strategy. First strategy is compact. The thread pinning follows the order of threads creation and only uses one NUMA node. Next, the sparse strategy distributes the threads equally among the nodes, one thread per node. The shared strategy aims to pin sets of threads that work on the same chunk to single NUMA node. The P3net monitors the threads, the use of combination researches to control the number of cores available for the OS to allocate the threads. This mechanism takes into account the data allocation across the NUMA regions, allocating core to specific nodes. The P3net uses a priority queue with the PID of the threads and the NUMA resource usage information. The P3net decides when allocate or release the core. Finally, in the random strategy, the array database threads are pinned randomly through the cores in all NUMA nodes. We generated 20 random allocations to verify if workload have different behaviors. In the results, we show only the strategy with the best performance. In our experiments, we used the two-array database Savim and SciDB with a selection operation named subarray. The subarray is a simple operation in an array data model. However, according to the query selectivity, may require processing all the chunks. The NUMA machine used in your experiments has two sockets. In processing queries, we run each array database with 20 threads, equal the number of physical cores in our architecture. We vary the workload by 1 GB with different numbers of chunks and 50 GB with varying the operator selectivity. Here are the results with 1 GB. In this experiment, we vary the number of chunks. The x-axis shows the strategies and the y-axis the speedup. Here we have the number of the chunk in each experiment. We can see that even though the strategies in the literature generally show a gain of speedup, the best result of the random strategy shows that we have a performance gain space of 47% because the strategies in the literature are not getting the maximum performance. Next, the result is repeated when we look at reducing remote memory access. In Savim, the reductions in remote access was almost 5 times, and SciDB in 3 times. When working with a 50 GB workloads, we kept the number of fixed chunks in 210 and analyze different operator selectivity. The exact carry selects only one chunk. We evaluated high selectivity and low selectivity queries on 3 chunk setup. Using just one chunk with high selectivity and low selectivity, on 20% of the chunks with high selectivity and low selectivity. Finally, with on many chunks with high selectivity and low selectivity. In this result, we observe that when we have high selectivity and the query is executed in almost all chunks, the speedup potential can be up 48%. Again, the results are reflected in memory access, reducing the remote access in Savime in 5 times and SciDB 4 times. Next, we analyzed energy consumptions by main memory. Understand that it's only part of the energy consumptions of the architecture. In the figure, we showed the energy consumptions in the experiments with a database of 50 gigabytes, normalized by the baseline. We can observe that the present behavior is similar to speedup results. The random strategy reduced the run energy by 52% in Savim, with the high selectivity in many chunks. For side B, the energy saving within the use of a random strategy was 31% high selectivity in many chunks. Finally, we confirm our hypothesis that thread pinning in the new architecture affects the CBRA operation performance. Traditional techniques are still far from the maximum possible gains, and static strategies only achieve 48% from the potential speedup and 26% of the energy saving. This work opens a new research topic in array database systems. And as future work, we intend understanding the new effects in other array database operations and design an array database scheduler that finds the best thread pinning. Thanks for your attention, and I will be glad to answer any of your questions.